A, B, and C are not necessarily distinct. So in addition to this test, A times B is equal to C, we're also going to test A squared is equal to C. So for example, if one of our subsets has a minimum element that's A and some other elements, then the minimum product of A and these other elements of T is A squared. The minimum value of our set S is 3. So let's see what happens when we allocate S to these two subsets. We're going to partition our set S into two subsets, T and U. And we'll start with our minimum element, which is 3, and we'll put 3 into set T. The minimum product in T is going to be 3 squared. Let's find our second set U such that the product of any two elements in a set is not also going to be in that set. And since A and B are not necessarily distinct, this includes A squared, cannot also be in the set. And we'll see how large S can be. Since we don't want 3 squared to be in our set T, we'll put it in our other set. Since 3 squared is in our set U, this means we can't have 81 also in set U. So we'll put this into T, and it looks something like this. We skipped 3 cubed. Let's see if we can put 3 to the third power into T. We already have 3 here, so if we multiply 3 to the first and 3 cubed, we're going to have 3 to the fourth, which is also in our set T, which means 3 cubed can't be in T, so we'll put it into U. So U is going to look something like this. Our next power of 3 is 3 to the fifth. This is 3 times 3 to the fourth, so we can't put it into set T. It's also 3 squared times 3 cubed, so we can't put it into U. So wherever we put 3 to the fifth power, we're always going to be able to satisfy the problem statement when M is equal to 243. If M is the minimum value that satisfies the problem statement for any partition, then no partition exists for M less than or equal to 242. So S is consecutive integers starting with 3, and we'll start with the subset A, and we'll put 3 in here. If this is our subset so far, the minimum product of any two not necessarily distinct elements is going to be 3 squared or 9. So we can take the consecutive integers from 3 all the way up to 8. So instead, we'll put 9 into our second subset we're calling B, and we'll keep on going, and we'll note again that in B, our minimum product of any two non-distinct elements is the square of the smallest element. Everything else is going to be bigger, and that's 81. So we can't have 81 in our subset B. So when we build out B, we'll start with 9 and 10 and all the other elements until we get to 80. The product of any other two elements in this subset is not going to be in this subset so far. So we will put 81 back into A. Here is A so far ending with 8, and then we'll skip up to 81. We note that the largest product of these first few elements is the square of this largest element, and we note that it's less than 81, so we're still good. So after 81, we'll continue with 82 and so on, and we'll see how far we can go. We've taken care of the product of all of these first 6 elements. The next largest product is going to be 3 times 81, which is 243, which means 243 cannot be in our subset A. So let's keep going with our set A, and we'll stop at 242. And as above, because 27 is in set B, we also can't have 243 in set B. We're able to split S into two sets that look like this, where M is equal to 242, and for anything less than 242. So we've confirmed that our minimum value of M is 243. If you'd like me to solve any other math contest problems, please leave them in the comments.